Hello and welcome back to the next installment in the series The Ray Tracer Challenge by James Buck. We are implementing a ray tracer using this book as a guideline and the tests in this book as a guideline while using Rust, or better said, while learning Rust, because I've never used Rust before and I've never written code in Rust before since starting with this book. Hello, just a short intermission from a little bit wiser and older Jacob, which by now has done some of those recording sessions and some more streams, and has realized he forgot to tell you that there are information in the description below regarding the GitHub repository where you can get all the code we are writing here to follow essentially along. Furthermore, please bear with me while I'm still learning on how to present all the different things I'm doing currently during the recordings. I get better from recording to recording, from session to session, so please be a little bit patient. And now, back to the program. Have fun. So yeah, let's work on that. In the last session, we actually implemented a lot of different matrix operations and stuff like multiplication of matrices and the identity matrix and stuff like that. We can furthermore now multiply, where is it? We can multiply a matrix with a tuple, or better said, a point. Essentially this implements multiplication. We have implemented multiplication with a tuple and only testing it here with a point, but should work with a vector as well as we did it the right way, and this test proves it. So, or we are quite sure that this test proves it. So now the next thing we are going to implement are the transpose function of a matrix. Transposition of a matrix actually is simply kind of rotating it. We are actually replacing the columns with rows and the rows with columns. So the first column gets will become the first row, and the second column will be the second row, and the third column will be the third row, and so on. So we should actually just be easily it should be quite easy for us to implement this. So let's, as always, do a test first, and let's start here by creating test, test, and we have an fn here, which we call, what do we call it actually? Transposing a matrix, simply. Yeah, makes sense. Transposing a 4x4 matrix. So yeah, let's see. What example data do we have here? Let m1 equal matrix 4 by a matrix 4f from followed by our array, and the first row will be 0, 9, an expected result here, which is a matrix as well, and it will be the transposed. So actual result be m dot transpose, and then let's do an assert fuzzy equal of actual result with expected result. And of course we don't have a transpose function yet because we haven't implemented one, but now we have the test, so a failing test, and now we're making it green, so we're making it successful by implementing. Where do we implement this? Let's implement it below here. Let's say we have a matrix for f and we want to implement an fn transpose on this one, which will actually result in a new matrix for f. And of course we need self for that. So, and it's public. And essentially it's quite easy. We are just wandering through this thing row and column wise and simply flip the information. So let's create a new matrix here. So matrix 4f new. We will have that, and we need immutable, of course. And We will return it in the end. So now in between, let's just do a for row, 1, 2, 4, for column, 1, 2, 4. We are actually doing the following. We are doing it like this. We are filling it column row wise by simply taking self row column. Missing in, oh yeah, row in. So this should actually already work out. Let's check this. Cargo, test, canvas, run, compiles, runs, tests, pass. Perfect. Let's commit this. We are already done with creating a transposed matrix. As I said, it's not hard to create a transposed matrix. Git add source matrix, git CI, implemented transposition of matrices. So maybe we could push it. That's in between. We could push it, and I could drink something here. Now the next thing we actually want to do is implement the inversion of matrices. So the inversion is actually something that we needed a little bit to talk about. The inversion is actually a matrix which, if you multiply a matrix with something else, with another matrix or a point, if you apply the inversion, or if you multiply it after this operation with the inversion of the first matrix, it will yield the original result. So it's something like if you multiply something with 5, the inversion of 5 would actually be, in normal algebra, would be a fifth. So if you multiply it with 1 divided by 5, then again, it would yield the original result. And with a matrix, that's actually the same, and it's the inversion of the matrix. Inverting a matrix is quite useful if you, for example, need to, you want to kind of do something like you have a camera movement, for example. You are going to most likely not do stuff like move a camera around in a 3D scene, but you are actually transforming the whole world perspectively seen from the camera. So if you are moving the camera closer to something, you are not actually moving the camera, you have a fixed camera and you are moving the world in front of the camera. So that would actually result in the same thing. But this is, for example, something where you would need the inversion of matrices, and especially with ray tracers, you need the inversion a lot if you are calculating intersections between lines and different things like, for example, spheres or objects in your scene. So we will use this a lot later on. But in order to implement inversion of matrices, we need to implement quite some other stuff first, because implementing inversion directly isn't that easy. So the book is actually moving us through different principles we are going to implement first. And the first thing we are going to implement is the determinant. The determinant, specifically, if I'm right, for a 2x2 matrix. Yeah. So what is a determinant? A determinant is a scalar value. So if you create the determinant, or you calculate the determinant of a scalar of a matrix, you get a scalar value, and it's actually, that's why it's called determinant. It's actually coming from the concept where you use matrices of coefficients in equality. Is it called equality systems? I don't know. So it's not equality system. What is it called in English? I don't know this mathematical terms in English. That's quite hard. Let me just check. Equation system. Yeah, that makes a lot of more sense. So if we have a system of equations which we want to solve, we could actually describe this in a matrix with the different coefficients in the different matrix columns. And if we then calculate the determinant of this matrix, we would get an information about if this system of equations is solvable at all or not. So if the determinant, for example, is 0, the outcome of this system cannot be determined because we don't have enough information in it. So that's actually something you can do with that. But we can use this later on to calculate the inversion matrix. So we will start simply by, creating a determinant of the 2x2 matrix. And by the way, creating determinants of higher dimensional matrices gets quite complicated. So we only do it for 2x2 here now because as far as I know, we only need it actually for 2x2 matrices. But let's not get ahead of ourselves. So let's just do this, and maybe we will just arrive at a point there shortly where we might be reconsidering the fact that we have different data types for our different dimensional matrices. But let's just not get ahead of ourselves. So let's work this out here. Let's write a test first. As always, we have this task calculating the determinant of a 2x2 matrix. Should actually work out as we are expected to. So let's just implement matrix 2f and let's implement determinant, which should be a public function, and it takes a self and returns an f64 value. And the determinant is actually quite simply, can quite simply be calculated for a 2x2 matrix. It is just, it is the first value of the first row, first column value, multiplied with the, I can never remember this. Yeah, over cross. So it's with the one in the bottom right there, minus the top right one. So 0, 1 multiplied with the bottom left one. So self. Oh no. Self 1. Oh, come on, self 1, 0. So this should actually be our determinant implementation. So let's actually check that. Cargo test. Let's run our matrix tests here and let's take a look. And it doesn't work out as we expected. So what's the problem here? Transposing a 4x4 matrix. Wait, what? I might be wrong, but didn't we run this before and it worked out? It worked? Wait a second, what? We have a whole bunch of the zeros here, which is definitely not what we want there, but what the hell has happened there now? Why did I change something here by accident? Let's I don't know. Maybe this would be the time to check how. Can we actually take a look at how a debugger would work with Rust? Let's check if there is a simple possibility to have something like VS Code Rust debugger. Native debugger based on LLDB. Yeah, okay, makes sense. Okay, we've already installed it. So that's nice. So now let's configure VS Code. Ah, nice one. And we are at this breakpoint. I like it already. So let's take a look what's happening here. We have some, we have self, which is data, which is it actually, let's take a look. Is this the right thing here? So this should be self. It looks to me that this is self and it looks quite nice. Okay. So M should be a completely 0 one. Yeah, that's nice. So now we are at where is it? There it is. Now we are at row 1, column 1. What? Row 1, column 1? Why? Oh! There we go. Found the error. Okay. So let's stop the debugging here because I think I know what I did wrong. It's 0 indexed, not 1 indexed. So I really did not run those tests, I guess, because now they are running. Yeah. Okay. So let's just let's fix this. Get ci -- amend, and let's put it into the last commit. I'm the only one using this repository, so a force push there isn't that bad. So yeah, we have this one there, and yeah, now I guess we can get back to no, git -pop. We can get back to our determinant calculation and check this out as well. So let's quit. I want cargo test matrix. Yeah, but I actually like that because now we have just quickly configured our IDE to do some debugging on the code, which we will most likely need later on. So I like that. And I like how easy it was that VS Code obviously detected the cargo information there and just created all of the run targets for us and stuff like that. I like that. So the Rust integration in VS Code seems to be really nice. Okay, so yeah, let's do the next step. The next step is actually submatrices. So what is a submatrix? Yeah, I think we can most easily, I can explain this using an example. A submatrix of a certain matrix is always a matrix with a lower dimension by 1. So the submatrix of a 3x3 matrix will be a 2x2 matrix. The submatrix of a 4x4 matrix will be a 3x3, and so on. Let's just create another test here, and then I will explain to you what a submatrix is based on this test, because I guess that is the most easiest way to do this. A submatrix of a 3x3 matrix is a 2x2 matrix, is the name of the test. So let's do this. Let's call this one M1. And we should write a let there, let M1, and this will be actually a matrix 3F. The expected result actually is then supposed to be a 2F matrix, of course. As I said, it is a dimensionless, and in this case, the expected matrix is, and the actual result is M, equals M dot submatrix 0, 2. So, and let me do the comparison here. Assert fuzzy equals actual result, expected result. So, let me explain quickly what. Let's fix this error, and then I can quickly explain what a submatrix is. A submatrix is so we got this matrix here, and what we wanted from the system was the submatrix 0, 2. So what we actually told it to is remove row 0 and remove column. Oops, sorry. Ah, no. And remove column 2. And if you look at this, this here is exactly our submatrix. So a submatrix is simply a matrix with a lower dimension by 1, where you remove a specific column and a specific row from the original matrix. So it's nothing really complicated. It just is something that needs to be built. So and we're actually going to implement this here now for our 3x3 matrix. So let's implement something for our matrix 3F. That's pub fn submatrix, and it will take a row, which is a U size, I guess, and a column, which is a U size, I guess, and it will return a matrix 2F. No, that's done like this in Rust. Yeah, and now we need to get the appropriate information out. We would first of all create a new matrix. We would first of all create let M matrix 2F new. We would start with that. We would have something here like a mutable U size source column equals 0, I guess. No, it needs to be this way. Yeah, I guess so. It needs to be this way, and we have source row, and let's put this there. So let's have another one here, which is the target row. It's U size, and it's 0 as well, and we have the target column with the same information. So now we have source and target rows and columns, and now we are going to while source row is less than 3. Yeah, we are doing something here, and while source column is less than 3, we are doing something here. And what we are doing here is while source row is less than 3, we are actually doing the following. We are incrementing source row after we have processed it. And if source row, the current source row, is equal to row, we just skip it. Source column, source row +1, skip removed, skip row to be removed. And what we are doing further along here is each time we have processed one row, we are source column, we are resetting the source column to 0. So this is what we are going there, and now in the source column we are doing the same thing. We are skipping the column if source column, which should be removed. And at the end, we are of course incrementing the source column because we want to move further along. And now what we can do here is we can have the matrix with a target row and target column, which we need to set in a second, is self source row source column. And we are returning the matrix in the end. Expected value self was, wait a second, we did not specify this here, so yeah, this does not need to be mutable. Oh, we did not declare this variable mutable. So now this is mutable, and yes, of course, now we would always store it in 0, 0. So what we need to do here as well is the same thing we are doing here with the advancing. We need to advance the target row and the target column. And we're doing this here as well. And I am really sure there is a lot cleaner and nicer way to implement this actually than I just did. There should be a lot nicer way to do this with properly set up loops, but my brain just, at this point, my brain does not allow me to do this. I will come back here and refactor this at some time. So let's create a to-do here. To-do, or fix me in this case, find algorithmic, find a nicer way to do this. So column node, the column wasn't, oh, that would imply that I did a wrong check here. If source column equals column, not source column. So thanks for the warning and for the check, Rust. So, okay, it failed. Index out of bounds, the len 3, but the index is 3. What? Thread, matrix, panicked at index out of bounds. The len is 3, but the index is 3. So we are actually running out of bounds there. Where are we running out of bounds? I see, because we are doing this check here, and then we are skipping over, and yeah, and we are not meeting the conditions. So I guess what we should do is essentially something else here. We should do this at the end. No, this would not work. I don't like that. Is there something like an until in rest? Can I do the... it would be a lot easier if I had the condition at the end of this. Yeah, let's check. Rust do until. Has no do while loop with syntax sugar, use loop and break. Yeah, I usually don't like this a lot, but yeah, it's... yeah, I guess we can do this. So let me do this here. If target row... No, wait, we could actually... We can do this a little bit better. We can do just like while target row is smaller than 2 and while target column is smaller than 2, then we shouldn't have a problem there. This should work. Yeah, it works. Okay, that at least makes things a little bit easier, and we are sure that we don't run out of the bounds of the target matrix, which is quite nice. And if we did nothing wrong, we cannot run out of the bounds of the source matrix as well, but yeah, it seems to me that this is right now. Okay, so now we have implemented a submatrix of a 3F matrix. And now we unfortunately need to implement this exactly the same way for a 4x4 matrix, but the algorithm will mostly be the same. I really don't like our matrix implementation that much because it is kind of scattered and complex, and yeah, I guess we can do it a lot cleaner if we would know how to do this in Rust. Not sure, but yeah. So, submatrix of a 4x4. A submatrix of a 4x4 matrix works exactly the same as with a 3x3, but it creates a 3x3 in the end result. So, let's define our matrix here. Can you already guess which row and which column we are removing? We are removing this row and this column. So let's create a submatrix based on 2, 1. And let's then have the system expect it. Of course, we don't have an implementation yet for submatrix on matrix 4F. So let's copy this implementation, as it will be nearly exactly the same, only with a slight difference in the guards there. So we will calculate this, but go there. We will create a 3x3 matrix as a result, and we will iterate 3x3, and this would actually, we should of course output a 3x3 there, and now we should be good to go. Let's run the tests, and yeah, this is working out. So even though I don't like the implementation, it is working as expected. Source matrix. Let's commit this. Implemented submatrix operation for 4x4 and 3x3 matrix. Oh, should put a -m there for message. So now we know we have a determinant and we have submatrix. Now we are talking about so-called minors. What is a minor? A minor is a combination of determinants and submatrices. Submatrices in a way. So a minor is if you take the submatrix of a matrix and calculate the determinant of this submatrix, you have what's called a minor at this point. So this is actually now what we are going to calculate and to do. So let's create a test for that. fn. Maybe I could... Let's try something, because usually I have the tests in another file, and then I have this file just split up right besides where I do the implementation. So usually I have my test on the right side and I have my implementation on the left, and even though it is the same file, I can actually easily achieve this by having the same file open in a split view editor, and I like this a lot better. The only problem is that in the recording, let me check, my head is there maybe in the way. I need to be a little bit cautious about that, but that would actually be easier for me to do. Maybe I could even move all this here in this screen area, but yeah, we will see. I will need to take care of this a little bit, but it would be a lot easier for me to have the implementation here and the test here. So what we are going to do is we are implementing something shortly here on the matrix 3f. So let's put our cursor there and let's implement our test now here to start. So calculating a minor of a 3x3 matrix is the test called. So let's, whoops, no, I don't want to see the problem. I want to calculate the minor of a 3x3 matrix. We want to assert that the determinant value we calculated is 25, and we want to assert that the minor we calculated is 25. So there is an exclamation mark missing there as well, and of course the minor. Did this? I hope you could read this while I was implementing it. Maybe it's not a great idea to have this here on the right side while implementing it. Maybe I will only leave the test open here, not while doing this, but only while implementing the corresponding code so that we can read up on this. So yeah, let's implement this pubfn minor, which will take a row, which is a U size, and a column, which is a U size as well. And it will return an F64 value. And luckily, we have mostly done all the work already. So what we need to do is, we missed give us a self-reference here. We are simply doing a self, and we are having it create the submatrix at the row and the column we were given, and then we are calculating the determinant of that, and we are returning this. And why the heck? Because I have a semicolon there. So, and now if we run this, cargo run no test matrix, let's see, it should work. Yeah, it works. So we have successfully calculated the minor of a 3x3 matrix. Now we have these minor values, we can start talking about cofactors. So cofactors are essentially the same thing as a minor, more or less, but they have the possibility of their sign changed for each of their values. So I guess we will see this once we implemented the test. Should I do this here now, or should I will try to do it below here, because I really like the way this is going to split up here and I don't need to scroll around all the time. So let's just check if this is going to do what I suppose it will. Let's implement the test then. So calculating a cofactor of a 3x3 matrix. a change here. Of course, it's a different value. That is to be expected. We have 25 here for the minor, but now we have minus 25 for the cofactor. And this is essentially the difference. The calculation of the cofactor is mostly the same. We are calculating the determinant, but essentially we are we might change the sign. What we essentially need for a cofactor implementation now is cofactor self row usize column usize. It's an F64, and what we first need essentially is, let's get this let minor, because we need the minor definitely, because it's the same thing essentially, but we need to take a look at how this thing works out with the minus and the plus. So essentially now the cofactor sign is changed if it is at a certain position. So if it is the submatrix calculation for a certain column and row. So if we are starting with a plus at the top left, and then we have plus, minus, plus, minus, plus, minus, plus, minus. We are iterating throughout all the rows. And so essentially we can easily find out what kind of sign change we have here by simply checking if row plus column is an odd number. And if it's an odd number, we need to multiply it with -1 or negate it. If we divide this by 2 and it is not 0, we actually have we have ourselves an odd column, odd value. So we are actually, then we need to return minus minor, and else we want to return minor. Or we can simply do, I like this even better, even value. So we are returning the minor and otherwise the minus minor. So yes. And let's check the tests. And they are passing. So we have correctly implemented the cofactor. And now that we have implemented the cofactor, and I'm going to commit this here, git status, git add source matrix, git ci, implemented cofactor calculation on 3x3 matrices, whatever. So now that we have all this stuff ready, we can actually calculate the determinant of a larger than 2x2 matrix. And as I said before, it is quite complicated to do that. So we started out with the 2x2, and now we are at a point where we are going to implement it for larger matrices by use of all those mathematical things we just implemented. So how is this going to work out? And we just go step by step by this book. We are going to write tests. So it is telling us to write 2 tests. Let's write those tests. It is telling us the tests to calculate the determinant of a 3x3 matrix. So the determinant should, in the end, should be 196. And it will be some sort of combination, actually, of those values. So yeah, so let's actually go ahead and implement this then by taking a look at the cofactors. And what we are going to do is calculating this cofactors for any given row or column and loop through them. And for each of the elements, we multiply the element's value with its cofactor and then add these products together. So this should be easy enough to implement, in which one we are here in the 3F, so we are here in the right one. So let's implement now, implement pub, no, wait a second, what am I doing here? Pub fn determinant, and I'm thinking about extracting all of those functions out into traits, like the cofactor trait and the determinant trait and stuff like that. I guess that would be the clean way to implement this. At least I would assume that. But yeah, for now we have this determinant and it's given self and it's returning an F64. And so we are actually, we have a let determinant is a mutable F64 here, and we will initialize it, I guess, with simply 0. And then we will start with for row in 0 to 4. So no, column, sorry, column, because we want to iterate the first row. So we are going to take the first row and iterate over each of the columns. So let's do this, I guess, and add up all those cofactor values. So what we are going to do is we are saying that we want determinant to be this one, which is self, and we want to get the first row with the column, and we want this one to be multiplied by self.cofactor row 0 column column. So mismatch type. Okay, so and we need to return, of course, the determinant here. So let's check out if this test actually works now. It does not. Panicked. At index out of bounds. Len is 3, but oh yeah, we iterated. We are actually in a matrix 3x3, not 4x4. So we iterated one. Okay, so this works. So now we can essentially just take this and copy it over into our matrix 4F implementation. And what we are going to do here is we are doing the same thing, but we are just iterating one further. And we don't have a cofactor implementation for our matrix 4F yet. We don't have a cofactor implementation for our matrix 4F? Did we implement minors? No, we didn't implement minors as well. Okay, so we need to implement this, but we can now implement it because we can now create determinants of I see, we can now create determinants of matrices of type 4, so 3, so we can actually more or less copy this here. So I guess if I now put this in here, it should recursively work as we have implemented the determinant on the 3f, and this should work, and so we can create and calculate the determinant on a matrix 4f. So let's at least try to compile this. Yeah, it is running. So now let's create a test here for that. Maybe I will try and figure out if there is a better way to do this in Rust. But first, let's implement the all famous, or what we were starting out to do, inversion of matrices. First of all, we need to talk about that not every matrix is invertible, actually. If we have a determinant of 0, we cannot invert the matrix. So there are certain matrices which cannot be inverted. Usually we won't have this problem because we will, in 3D conversion, we will most likely work with matrices which are invertible inherently by their kind of creation process, because we are putting different operations together, like translation, like scaling, like rotation and stuff like that. And we can invert all those, so that's not a problem, but we need to make sure that we can check for this. So as before, we will only implement the inversion on 4x4 matrices now that we have everything ready for that. But first, let's implement a pubfn is invertible, because this is something we might want to know, and we should write a test for this then as well. The book instructs us actually to do. So as I've said, we can simply return self. Let's get the determinant is not 0. We might want to determinant fuzzy eq, or better said, fuzzy not equal 0. Mismatch type expected reference to. Okay. Then we give it a reference to that. I can live with that, even though that does not make sense in my opinion here. And let's create a test for this as well. So I guess we will have a test here, which is then called fn testing an invertible matrix for invertibility. Yeah, isn't that a nice naming there? So, and we assert equality, or no, we assert M is invertible. So this should work out. And now we copy this test again and call it testing. And is it then called non-invertible matrix for invertibility? And we change this matrix completely. So, and we are assuming that it is not invertible. So now let's have a look at these tests, and they pass. Our is invertible actually works out. So calculating the inverse of a matrix will use everything we've used before. We've implemented before. So let's create a test for this, I guess. Fn calculating the inverse of a 4x4 matrix. Yeah, and we will have a let expected result be the following matrix, and this will not be fun at all writing it writing it down now. So M and say inverse. Inverse or invert? How is this function actually? It's called inverse. So yeah, it's the inverse of the, yeah, it makes sense, I guess. So let's get the inverse and then let's assert fuzzy equality. The actual result is essentially the expected result. Yeah. And let's assert certain other things which the book tells us to do. So we are doing it. And those are all the tests we are supposed to have there. So now what we actually need is to implement the inverse. Public function inverse self returning us a new matrix for f. And the first thing I really want to do here is if self dot, if this thing is not invertible, we are simply panicking out of here because then something really went wrong. Matrix is not invertible, but inverse was called. There we go. Let's just panic out of this thing. So otherwise, let's create a new matrix, the inverse thereof, or what will be the inverse. It needs to be mutable, and we are going to create simply a new one here because we are now filling it with data. And later on we are returning it. So let's return it here. So now how are we going to do this? The inverse actually is something like if we actually create a matrix of cofactors for each of our columns and rows. Yeah, so we would loop through all of this stuff and then calculate the cofactors for each of those. Then we are going to transpose the matrix, and then we are dividing this whole thing by the determinant of the original matrix. And what we get out then there is the inverse we are looking for. We could of course now implement all those different steps, and I kind of would like to do it, but matrix multiplications are used a lot and a lot and a lot, and the inverse of the creation of inverse matrices is used a lot as well. So maybe we should do it more efficient then, and it isn't that hard to read actually. Let's do this. We are iterating over our rows, I guess. Start there to, where are we? 4. Oh, sorry, there's an in missing. And in there we are iterating over our columns from 0 to 4, I guess. And then we need to calculate our cofactor, I guess, which we definitely need. Yeah, we definitely need that. Yeah, let's just calculate the cofactor at the at self.cofactor row column. Oh, did I call it col? Well, why did I call it col when I called it column everywhere else? I like this more explicit. So now we have the cofactor, and now we should be able to, we should actually have this let determinant is the self determinant, I guess. Yeah, because we need that a lot and we don't want to calculate it every time. I'm not sure that it is optimized away. Maybe it would be. I have no idea. So let's just do then we have this, we are storing this transposed, so column row, and we are then storing there the cofactor value divided by the determinant. And let's make a note here, store transposed transposed storage. Let's do it like this so that we will remember that later on. So this should actually then, with everything else we've implemented before, calculate the inverse. And I guess we're going to check that. And even though the tests are running fine, we have a warning in there where calculating the inverse of a 4x4 matrix, dead code. So maybe the tests aren't running because I've somehow not put this test flag here. So now let's try again, but they are running. So there should be, let me do a matrix, or let me just do an inverse here, and it should run one test calculating the inverse of a 4x4 matrix, and it is running fine. So yes. So yeah, we have effectively implemented inversion. This is quite nice. Now we have an inversion of a matrix. I guess we should maybe create another test here, which is to check if the inversion actually recreates the original. So yeah, so let's actually implement that as a test before we are finishing this this chapter here. Yeah, let's do the test annotation, which will be here, and have multiplying a product by multiplying a product by its inverse. So we need two matrices for this, of course. So we are going to create let M1 equal let M2 be a matrix for F, which is actually from let M3 be M1 multiplied by M2. We have implemented that, so that should work. So then we want let actual result then be M3 multiplied by the M2 inverse. So now we are asserting that that the actual result is the same as the initial M1. If everything works out as we expect it to, the multiplication of M3 with the inverse of M2 should actually make or roll back this multiplication, and then again should produce exactly the initial result. So let's check that. And it's running and it's working, and I like that. So as we can see there, multiplying a product by its inverse actually creates the original matrix again. And this is exactly what we wanted there. So yeah, I guess this is a nice cut point, as we have now finished the second chapter, and the next one actually will be matrix transformations, and we will there use all of those different math foundations we've created now in order to calculate a lot of different stuff, to create a lot more awesome actually applications for this by creating transformation matrices, which then will allow us to transform things in the three-dimensional space by rotating, translating and stuff like that. And we need a lot of that later on to describe certain geometry in space, to move it around, to calculate intersections with it, which is the main work a ray tracer does. So we will need a lot of that, and we will do this in chapter 4 actually by implementing all this from our nice The Ray Tracer Challenge book. And yeah, thanks for joining me again for this implementation of chapter 3 of this book. And if you liked it, please give it a thumbs up, and don't forget to subscribe if you want to be informed of further videos I'm posting to the channel within this series or other series I'm planning for future. So yeah, thank you again, and have a nice day. Bye. See you the next time.